Logarithmic differentiation. Our objective in this lesson is to find the derivative using logarithmic differentiation. When do we use logarithmic differentiation? If the function consists of products, quotients, and powers, we can take the natural logarithm of each side and simplify using properties of logarithms. Let y equal x squared times the square root of the quantity 5x plus 1 divided by the quantity 3x minus 2 cubed. Find dy dx. Now if we just take the derivative of this, it will require a product rule, a chain rule, and a quotient rule. So we could do that because we know all those rules, or we could make it a bit easier on ourselves. We can take the natural log of each side. Why does that help us? Well, let's see. The natural log of the left side looks like this, natural log of y. And then the natural log of the right side looks like this, natural log of x squared times the square root of 5x plus 1 over 3x minus 2 cubed. At first glance, it looks like it's made this more complicated. But because this side is now a logarithmic expression, we can simplify using properties of logarithms. Remember our properties of logarithms that are really important to know. The left side, of course, I'll rewrite, natural log of y. And on the right side, I have a product, I have a power, I have a quotient, I have another power. So these three properties come in very handy. Let's split this up. Natural log of x squared, which of course the 2 in the exponent can go in the front as a coefficient using that power property, plus, because this is a product, the natural log of 5x plus 1, which would be to the 1/2, but again, using that power property, I'll write that exponent as a coefficient of the log, minus, because I'm dividing, the 3 for the exponent, right away I'm going to put in front, natural log of 3x minus 2. Now it looks like we've made things more complicated because there's so much more, but we have individual terms that are simpler than that one original entire expression. Now I take the derivative of both sides of the equation. The derivative of natural log of y, 1 over y times dy dx, using my chain rule, equals 2 times the derivative of natural log of x is 1 over x, plus 1/2 times the derivative of the natural log of 5x plus 1 is 1 over 5x plus 1, using the chain rule, times 5, minus 3 times, now the derivative of natural log of 3x minus 2, 1 over 3x minus 2. Using the chain rule, the derivative of the inside is 3, so times 3. Now, the right side of this, I can clean up a bit. Let's rewrite what we have on the left, 1 over y times dy dx. 2 times 1 over x is 2 over x, plus 1 times 1 times 5 is 5. 2 times the quantity 5x plus 1, minus 3 times 1 times 3, 9 over 3x minus 2. Remember, my goal is find dy dx. I have dy dx, but I need it to be by itself. So finally, I'll multiply by y to get rid of this 1 over y, or divided by y. So dy dx equals 2 over x plus 5 over 2 times 5x plus 1 minus 9 over 3x minus 2, and all of that times y. Now, this is an acceptable answer, but we can even do better than that because remember, they express to us what y is in terms of x at the beginning. So let's rewrite what dy dx is, all in terms of x. 2 over x plus 5 over 2 times 5x plus 1 minus 9 over 3x minus 2. And then instead of times y, we'll write what y is equal to. X squared times the square root of 5x plus 1 over 3x minus 2 cubed. Now there are other ways to write this expression, such as all in one fraction, for example, but we do have a derivative. It's all in terms of x, and it will be useful to us. Let y equal x to the x. Find dy dx. Now notice there is x in the base and x in the exponent. This expression is neither of the two forms that we know how to take derivatives of, such as y equal x to the a, where a is a constant, and the derivative y prime is just the power rule, a times x to the a minus 1. It is also not y equals a to the x, where the base is a constant and the exponent is a variable, and the derivative y prime is just a to the x times natural log of a. This has variable in the base and variable in the exponent. So this is an example where, because it's neither of these things, we must use logarithmic differentiation. There's no other way to do it. So let's proceed. We start by taking the natural log of both sides of the equation. Natural log of y equals natural log of x to the x. Why does that help us? Because now on the right side, we can use our properties of logs to rewrite this so there is no x in the exponent. Natural log of y equals x times natural log of x. Now notice, when we take the derivative, we have a product of functions of x times natural log of x. So we want to remember using our product rule, fg prime plus f prime g. Let's start on the left side, taking the derivative of natural log of y implicitly. 1 over y times dy dx equals, using our product rule, we have f, the derivative of g, 1 over x, plus f prime times g, natural log of x. Now I can simplify. 1 over y dy dx. X times 1 over x is 1, plus 1 times natural log of x, natural log of x. Now remember, my goal is to find dy dx. So finally, I want to get rid of the 1 over y. I multiply both sides by y. So dy dx equals 1 plus natural log of x times y. But remember, I know what y is in terms of x. So a better answer is going to be 1 plus natural log of x times x to the x. And now I have my derivative in terms of x. Thanks for watching.